Good evening, everyone. I, Dr. Ganeshar Chate, Associate Professor, Mechanical Engineering Department at KLS Institute of Technology. On behalf of KLS Institute of Technology, we welcome you to this development program sponsored by the AICTE Training and Learning Academy, that is ATAL. It is a pleasure to have you all with us today for this exciting and insightful FDP on microwave processing and 3D printing of functional materials, from fundamentals to future technologies. I would like to invite Dr. Harshit Kulkarni, the Head of Mechanical Engineering Department and Associate Professor at KLS Institute of Technology, to share his introductory remarks. Please join me in welcoming Dr. Harshit Kulkarni.
Hello everyone. Am I audible, Dr. Ganesh?
Yes, you are audible.
Yeah. Yes. Respected Principal Dr. M.S. Patil, Dr. Vinayak Malik, Dr. Ganesh, respected resource persons, participants from various colleges and support staff. I, Dr. Harshit Kulkarni, deem it an honor and pleasure to welcome you all once again for this faculty development program on 3D printing and functional materials. This faculty development program is going to offer a wide range of benefits for all of us academic professionals, including professors, lecturers, and all of us. The key advantages will be enhanced teaching skills, updated knowledge, and we are going to have various research opportunities by collaborating with each other, networking, and the career advancement. We at the Mechanical Engineering Department, with the excellent support of management, principal, and my entire faculty team, are hosting this FDP for the benefit of each and every one of you all. In fact, various other initiatives that we have taken at the department include establishment of various centers of excellences, like Center of Excellence for Microwave Heating and Applications in association with Enerzi Microwave Systems Industry, Center for Additive Manufacturing, Center of Excellence for Multidisciplinary Design and Innovation in association with Dassault Systems, Center for Composite Materials in association with Vega, and we are also upcoming in the pipeline Center for Precision Manufacturing. Yes, we at the department are providing these centers of excellence for enhancing our faculty skill sets, in turn train our students to be ready engineers for the upcoming challenges in the industry. Yes, one of the best outcomes of these centers of excellences with the support of ATAL is what we are witnessing today is this 1 week faculty development program. Yes, mechanical engineering is growing in all fields and it is growing leaps and bounds. It is augmented with various technologies. Attending such an FDP offers a wide range of benefits for each one of us, and it will definitely help us in enhancing our personal skills as well as professional skills. Specifically talking about microwave heating and 3D printing of functional materials, these are the two advanced technologies that are increasingly being applied in various industries. Here is an overview of benefits of each. Benefits of microwave heating include energy efficiency, faster heating, uniform heating, reduced thermal stresses, and also it definitely improves the material properties. And yes, it is environmental friendly. Now, the functional materials offer customization and complex geometries. It offers enhanced material efficiency. 3D printing can be combined with this technology. And yes, we are going to have a cost-effective, low volume, and better production. And yes, it will also reduce the lead times. To be specific, in brief, combining this microwave heating with 3D printing of functional materials, the combination of this can further enhance the manufacturing process, particularly for materials that require specific thermal treatments during or after printing. Yes, for example, faster curing, sintering, and enhanced material development. I am definitely sure that all of you are going to have best of this 6 days of workshop wherein you will be learning about microwave heating embedded with 3D printing, and it is going to lead us even more optimized and innovative outcomes, especially in industries such as aerospace, automotive, healthcare, and electronics. I thank my management, principal, and the entire team for taking such an excellent initiative at Mechanical Department, KLS GIT. Once again, I welcome you all for this faculty development program. Thank you, and let us have a great days. Thank you.
Thank you, Dr. Kulkarni sir, for those insightful remarks. Now it's my honor to invite the principal of KLS Gupta Institute of Technology, Dr. M.S. Patil sir, to deliver the presidential remarks. Let's welcome Dr. M.S. Patil sir. The round of applause.
Very good evening to all present. Uh, the participants, participants for this FDP on microwave processing and on microwave processing, 3D printing of functional materials, from fundamentals to future technologies. Professor Virat Malik and Professor Ganesh Chati, HOD of Mechanical Engineering, Dr. Lakshmi Kulkarni, and my dear participants. First of all, I would like to thank AICTE-ATAL Academy for giving us the opportunity hosting this 1 week FDP on the futuristic technologies under mechanical engineering. Yes, mechanical engineering is progressing and evolving, and these are the days when we should make use of the latest technologies available for the processing of the materials as well as joining processes. As mentioned, fuel is one of the energy sources which can be used for the heating and joining of the components, be it with metal and be it with non-metal as well. This will reduce the stresses. At the same time, they will be energy efficient as well as the strength of the joint can be also improved. And we are in tie-up with, in association with one of the industries here, and we are conducting research on micro, and it has yielded very good results. At the same time, under manufacturing, the additive manufacturing or 3D manufacturing is the latest trend in the manufacturing processes, and therefore, giving a more aspect of the 3D printing as well as microwave processing will enhance our capabilities and capacities in the direction of mechanical engineering processing of the materials. I wish that the deliberations of this 5-day FDP will be more fruitful and everyone will have good takeaways and share this knowledge with their faculty members and students at their institutes. I wish this FDP a great success. Thank you. Thank you.
Thank you, Dr. M.S. Patil sir, for your inspiring words. To conclude the inaugural session, I would like to propose the vote of thanks. It's my both honor and privilege to stand before you today as we conclude this inaugural session of Faculty Development Program on microprocessing and 3D printing of functional materials from fundamentals to future technologies. On behalf of KLS Gupta Institute of Technology, I would like to extend my heartfelt thanks to all the distinguished KLS management, our respected principal sir, faculty, and all other participants who have taken the time to join us for this event. So, and that brings us to the end of our inaugural session. We look forward to an engaging and enriching week ahead. Thank you once again and enjoy the session. Shortly, we'll be starting our first session by Dr. Chandrasekhar sir at 6:30 p.m. in another 5 minutes.
Sir has already joined.
Okay. Next slide. Yeah, we'll start the session as Dr. Chandrasekhar sir has already joined the Google Meet link.
Yeah.
Yeah, it's my honor to introduce you our respected speaker of today's session, Dr. B.K. Chandrasekhar. He has completed his PhD in the University of Pennsylvania, United States, and he has completed his Masters in Material Science from IIT Kanpur. He has done his BSc and MSc from Bangalore University. He is currently advisor to Enerzi Microwave Systems Private Limited, Belgavi. He was a guest faculty for MBA at CBSMS, Bangalore University. He was the director at Laird Technologies India Private Limited, Bangalore. He was the technical director for John F. Well Technology Center, Bangalore. He was the deputy general manager at Ceramic Technological Institute, PHEL, Bangalore. He was research associate R&D Center, Grandwell Norton Limited, Bangalore, and he was also a postdoctoral fellow from 1981 to 82 in the Indian Institute of Science, Bangalore. His accomplishments are expert member in Indo-Norwegian Program on Environment, ex-secretary Indian Ceramic Society, Bangalore chapter, ex-secretary Material Research Society of India, Bangalore chapter, ex-member Divisional Scientific Committee, National Aerospace Lab, Bangalore, member Indian Society of Lighting Engineers, honorary invited faculty at Indian Institute of Science, Bangalore, adjunct faculty at MIT, Manipal, and a best faculty for addition engineers during 2004 and 5 at JFWTC. He was honored with this particular award and invited lectures at Confederation of Indian Industries, New Delhi, ITC Kolkata, Global Investors Meet, Bangalore, and NTPC, New Delhi. Publication in peer-reviewed reputed journals, and he holds several international patents. It is great to have you with us, sir. So we'll begin with session 1 from Dr. Chandrasekhar, sir. The session 1 is on fundamentals of microwave materials processing. Over to you, sir. Thank you.
Yeah. Namaste. And good evening to everyone, especially to Dr. Vinayak Malik, who has been coordinating this particular event with me for some time extremely well. This particular talk was supposed to have been given by our Managing Director, Sri Prakash Muguli. For some emergency, he is not able to be present today. So on his behalf, I will be presenting this talk. Just give me 2 minutes and I will try to open up my file into this thing, and let me see, I may have some problems. So give me some couple of minutes, okay?
Yes, yes.
Are you able to see it? I'm having some problems, so I'm not able to share the file. Can you see it, sir? Hello?
Are you audible, sir?
Yeah, I'm hearing you, but are you able to see my screen?
PPT open. Kindly open the PPT, sir.
Okay, just 1 minute. Yeah.
Yeah, now it's clear.
Are you able to see?
Yes.
Yeah, sure.
Great. Okay, great.
Can go in presentation mode, sir. Presentation. Yes, sir.
Okay.
Perfect.
Very good. Okay, sir, I'm just on time. Thank you very much for your cooperation. Prakash Mugli is the Managing Director of Enerzi Microwave Systems. I think most of you, especially in Belgaum, do know him very well because he is one of the internationally acclaimed expert on microwave technology. What I am going to do is that since there are 2 talks by me today, in the first presentation of Prakash Muguli, I'm going to give only a very brief highlights or an overview, and I will come to the finer aspects in the second talk. Okay. First of all, what exactly is microwave heating, and why it is used should be of immense interest to many people, because this is in India, this is relatively a new topic, not very well known to a large number of people in different sectors. First of all, this is a energy efficient method of drying or heating any object. Okay, as you know that as you go to higher and higher temperatures, the cost of energy increases, and India is always a energy insufficient country. Therefore, any amount of savings that we do in energy is a plus point for us. Second thing is that it enables a very rapid and very uniform heating of objects, which is not usually possible by conventional techniques. Normally, when we use a furnace, a resistance heated furnace, the rate of heating will be 10 degrees per minute or 20 degrees per minute, or even sometimes very less. But in the case of microwave, we can go to extremely fast rate of heating, almost to the extent of 200, 300, 400 degrees centigrade per minute. Okay, so it's a very, very rapid method of heating objects. Another problems that we have in conventional heating is that as and when the object or the material or the sample becomes larger and larger, it is very difficult to get uniform heating. Okay, the surface of the object will be always be at a much higher temperature than at the interior of the sample, and in many materials this gives rise to what is called as distortion in the sample. With microwave, this problem can be extremely minimized. The third important point is that there is always a need for improving the properties of the materials. And over the years, people have found that when they use microwave energy for heating materials, there is a tremendous improvement in the properties. We will talk about this a little bit later. What is possible with conventional method, whatever properties that we get, for example, like hardness, okay, or transparency, or capacitance of a material, all these properties can be improved by using microwave heating. And the last point is extremely important. There is a global effort to reduce the carbon impact in our processes, and any amount of work, even if it is negligible, to protect the environment is always a welcome step. And microwave energy gives impetus for this environmental benefit by reducing the carbon footprint. And we will talk about all these things in due course of time. I hope my accent and pronunciation is clear to everyone. Once in a while, I will give some time for you to ask questions. So please feel free to ask any doubts or questions, even during the midway of the talk. Am I clear in my voice?
Yes, sir.
Thank you. Now, what exactly is microwave material processing? As you all know that the definition of microwave approximately belongs to a frequency range of 300 megahertz to 300 gigahertz. Okay, so it's a wide range, and in this region is called as the microwaves. And of course, the majority of the frequencies that are used is basically for communication purposes, like our mobile phones, radar, and many other things. But for drying and heating purposes throughout the world, only two frequencies are allowed. One is at 2.45 and other one is at 945. Okay. 2.45 gigahertz, and the other one is 945 megahertz. And only these two frequencies are allowed for industrial purposes of heating and drying. And over the years, a large number of different sectors, including ceramics, polymers, metallurgy, composites, food processing, even waste disposal, and many, all possible sectors, one can use microwave very efficiently and at a relatively lower cost. More and more experience. Hello? Yeah.
Yeah, screen sharing, I think you have switched it off. Can you just share it 1 second?
No, I have not switched it off anything. I don't know. It went off?
Sir, just select the screen, sir. Just,
Okay.
select the screen.
White screen.
Presentation screen.
Is it coming?
Not yet, sir.
Let me, black screen. Coming? I don't know what happened.
Again, one stop and start, sir. Stop sharing and again restart.
No, last viewed. Not coming?
No, sir, not yet.
So there is a black screen and a white screen. White screen is there. I click on white screen. And
Stop sharing your screen once again, and then again.
okay. Let me go do that. Actually, 1 minute. Okay. Okay. It's coming now?
Yeah, your screen is visible. Yeah, now you can go to the screen, sir. Yes. I request participants not to just disturb the flow of the presentation. There was one participant who had shared his screen, because of which this screening has stopped. Anupam Jain, that's what I had noticed. So please don't disturb the flow. Yeah. Yes, sir.
Okay. Now it's all right?
Yeah, all right, sir.
Okay, thank you. Because I did not do anything to my computer, so I am not very good in some of these things, so please bear with me. So I was talking about the lower carbon footprint and other things. So this is a very well, basically microwave can be used for any sector where there is a requirement of any type of heating, okay? And the normal way of heating is typically, if it is a foundry type of application, people use induction heating for melting metals and so on. For ceramics and other materials, people use resistance heating. Even for polymers, they do use resistance heating only, like in an oven and things like that. So in what way the microwave is superior over conventional heating? As I mentioned earlier, that it is an extremely fast method of heating. Therefore, your process time is very much reduced. There are applications where the process time can be reduced from 8 hours, 12 hours, 14 hours from conventional time to less than 1 hour, okay, using microwave. So that gives you a tremendous amount of higher productivity and throughput without compromising on the quality of the product or on the cost. And it is a very highly energy efficient method. Let me elaborate a little bit on this point also, that in a conventional furnace, you put your sample, let's say, in a crucible and something like that. And then there is a wall of the furnace is with bricks, high temperature bricks, because you don't want the radiation to come outside, because the skin of the furnace should not be at a elevated temperature. So there are insulation bricks or fibers are used inside. So when you want to heat the material, you are heating not only your sample material, but also you are heating the crucible, you are heating the brick, the entire oven is, the furnace is getting heated. Whereas your objective is only to heat the sample. And therefore, the amount of energy that is used in a conventional method is very high. In the case of microwave heating, only your material gets heated, sometimes a little bit of the crucible only, where the thermal mass is therefore is reduced by, I would easily say by 70 to 80%, the thermal mass is reduced. Therefore, the total energy consumed is very much less. The third point I am talking about is what is called the volumetric heating. I will give examples of all these things later. Now I am just talking very high level overview only. When you heat a sample, especially which is very small in size, let's say a few millimeters or 1 centimeter or something like that, smaller samples, it is easy to get uniform heating across the sample. But as the sample size increases, you will find that the surface of the sample which is getting heated is always at a much higher temperature compared to the interior of the sample. Okay. Therefore, there is a thermal gradient present in the sample, and in many systems, this will make the object or the sample distort. For example, if you are heating a cylinder, let's say a small cylinder of a ceramic material, and when the volume is, when the volume of this sample is quite large, the one side gets heated more than the other side. Therefore, the perfect cylinder which you have pressed and put it in the furnace before will not be very uniform. One side the diameter will be more than the other side diameter will be less. And dimensional accuracy is very important in engineering applications. So this is not tolerated. And in microwave heating, because it is what is called the volumetric heating, there is a uniform heating of the sample. Therefore, such distortions are not present. Or even if it is present, it is extremely small, which is sufficient to meet the engineering requirements. And as I have already mentioned, it is a very eco-friendly, because there is no carbon dioxide emission from the process and things like that. Now, just this is a summary of some of the things that I have already talked about it. As I mentioned earlier, that we only use 2.45 gigahertz. That's the one particular frequency that is normally allowed in India for this particular type of application. We call the heating method as a dielectric. This is basically based, this method is based on what is called as the polarization of the samples. And we will talk about it either in this talk or in the next talk, little bit more in detail about the principal method by which this microwave interacts with the material so that the heating takes place. Third thing is it's a non-contact material. The sample is not coming in touch with heaters and things like that. And it can penetrate thicker sample also quite well. And it is a non-ionizing radiation. That means there is no such thing as a risk involved like a cancer in other things. And there are a lot of microwave myths associated. And I would like to spend some time on this also a little bit later. Now let us understand what exactly happens when microwave radiation is incident on a sample. Microwave is very similar to that of light only. Therefore, the incident microwave radiation either can get reflected or transmitted, or it is absorbed in the material. Okay, just like light, and it can also get scattered. All these three mechanisms do take place. Typically, metals have a tendency to reflect the incident energy of the microwave, and therefore once it is reflecting, the sample will not get heated. Okay, so metals is a somewhat of a challenge to use microwaves, but still this problem can be overcome in certain techniques, and I will talk about it a little bit later. So metals can also be processed using microwaves by some modifications. Second thing is, typically plastic materials can get transmitted because they are transparent to microwave, so nothing is absorbed. Again, the heating can be doesn't take place. If you take, for example, water is absorbs microwave energy very well, and therefore it is very widely used in cooking applications. Okay. Then there are other materials like ceramic materials. Ceramic materials are what is called the dielectric materials. They are electrically and thermally insulating, and depending upon the electromagnetic properties of these materials, the samples can get reflected, transmitted, or absorbed. And most of our presentation later is based on such dielectric materials. Water is an exceptionally good microwave absorber, and hence it is very widely used for cooking applications in a big way all over the world now. Now, earlier I talked about uniformity of temperature, and this particular slide gives a schematic view of what exactly happens when this yellow object that is present is heated, let us say, from a heating element as in a typical furnace. So as the infrared radiation hits the sample, the surface of the sample gets heated very fast, but as you go to the interior of the sample, the temperature becomes less and less unless it reaches a equilibrium temperature after a long time. Okay, then the difference in temperature from the surface to the interior is minimized. Typically, this will take 2-3 hours or more, depending upon the nature of the sample. Okay, so this differential heating or differential temperature leads to the distortion of the sample in many cases. Whereas in the case of the microwave, it penetrates the sample inside. Therefore, the difference in temperature from the surface to the interior is very much reduced or almost non-existent. In fact, in microwave, the surface is slightly cooler than the interior of the sample. Okay, this coolness at the surface, lesser temperature at the surface happens mostly because of the surrounding atmosphere, the surrounding parts of the surface is cooler, therefore it becomes cooler, whereas the inside it is thermally insulated, therefore it becomes very hot. So this gives you an idea about why the microwaves provides uniform heating and uniform temperature in the samples. This is extremely important as the sample size becomes bigger and bigger. Now, let me talk about the main. We have talked about a lot of things about conventional heating and microwave heating, and this slide gives a comparison between the microwave heating and the conventional heating. Okay, as I just mentioned, it is an internal volumetric heating, whereas the conventional heating is external surface heating. Heating speed is extremely rapid in microwave heating. As I mentioned earlier, that rate of heating can be as high as 300 to 400 degrees centigrade per minute, provided the sample can withstand it. Whereas in conventional heating, typically it is of the order of 10-15 degrees centigrade per minute. The energy efficiency is very high in microwave heating, almost to the extent of 80 to 90% in some cases, because only the sample gets heated and the surrounding crucibles, the insulating materials or any other thing is not getting heated. Therefore, there is a tremendous amount of energy savings compared to conventional heating. And in some cases, you can heat only a portion of the sample selectively rather than the bulk of the sample. which is not possible in the case of conventional heating. And again, the uniformity of heating is much better in microwave heating compared to conventional heating because of the volumetric heating mechanism that I explained earlier. Now, before I go further, I would like to know whether there are any questions.
Sir, I have one question regarding the whatever you have said in the slide number. I think observing, reflecting, and passing through it.
Yeah, yeah,
This one, sir, this one.
yeah.
Whether this is applied with respect to the composites, or what kind of things apply? Whether it is reflect or transmit or absorb with respect to the composite material.
Yeah, in the case of composites, let us say if you are using a ceramic composite or a metal composite, okay?
Yes.
Metal composite, definitely it will reflect, okay?
Yes.
But if it is a ceramic composite, depending upon the electromagnetic parameters of the material, which I will talk about it later, okay?
Yes.
It can get absorbed also. And even if it is not absorbing, there is a method to overcome the problem, and I will talk about it later.
Yes. Yes.
Okay. So basically, I would say, irrespective of the material, it is possible to heat many materials using microwave.
Sir, whether this microwave heating process, whether we can apply with respect to the fiber reinforced composites also? Because
Yes, sir.
the epoxy, whatever we are going to use, maybe with respect to the heat, it may melt sometimes, right?
Yes.
I hope. So that's why whether we can apply this process with respect to the fiber reinforced composites.
Yes, sir. I will talk about it later. Okay.
Yes.
I
Yes.
will
Sure.
talk about it. Okay.
Yes.
Any other question? Okay. I'll proceed. Okay. Now, if I look at, I keep talking about electromagnetic properties. Okay. Basically, there are 2 or 3 electromagnetic properties that are very important for microwave applications. One is called as the dielectric constant epsilon. Okay. This epsilon is a measure of the capacity of the material to store energy, store charges. Okay. And the other one is what is called as epsilon double prime, sometimes called as epsilon 2 also, which provides the amount of heating that can, because of the absorption, it will get transformation takes place from absorption to high temperatures. Okay. So epsilon 1 and epsilon 2, sometimes called as epsilon prime and epsilon double prime. Okay. These are the 2 important parameters of importance, which one should know when you are dealing with microwaves. Okay. And this slide gives these 2 parameters are dependent on not only on the wavelength of the material or wavelength of the microwave, but also on the temperature. This graph provides an overview of how the dielectric constant epsilon 1 or epsilon prime varies with temperature as well as with frequency. Okay. And as you will see that as the temperature is increased from 0 degrees to 20 degrees, 60 degrees, 80 degrees centigrade, the dielectric constant becomes lesser and lesser. That means the capacity of the water to store charges is very much reduced. Okay. And at the same time, when you see the graph for the epsilon 2 or the epsilon double prime, which is in blue in color, let us consider 20 degrees. Okay. So 20 degrees, the maximum absorption takes place at about, let us say, this is about 10 or 11. Okay. Because this is a logarithmic scale at the top. So this will be about 10 or 11. Okay. So the maximum amount of absorption by water at room temperature of the order of 20 degrees centigrade takes place in the region of about 11-12 gigahertz. Okay. So, but our cooking ovens in the house always operate at 2.45 gigahertz, right? So there is a mismatch. That means one may say that our cooking oven is not optimized, but that is not a correct statement. The reason for that is shown in the next slide. Okay. If the absorption is very high, then the penetration of the microwave into the interior of the meals that we are preparing is very much reduced. Whereas if it is at a different frequency on either side, then the tendency for it is to penetrate further is always there. And therefore, depending upon the amount of water in the food, the penetration of the microwave for 2.54 gigahertz, okay, becomes better and better with lesser water, and it is absorbed at a very thin layer when it is too much of water. Okay. So in almost our cooking, typically I would say that 2 to 3 centimeters is the type of containers that we have where the food is cooked in a microwave oven, especially when it is a solid food or with a lot of water. But for pure water, it doesn't matter because there is a convection current, and therefore the water absorbs very quickly, and there is a heating of the water very fast. Okay. And this is the reason why because of the penetration depth that is involved for the microwave, the frequency that is chosen for cooking food is not at 9, 10 or 11 gigahertz, but it is at 2.45 gigahertz. Now, there are a lot of myths associated with microwaves. I'm sure you all would have heard sometime or the other on this point. Does anyone know about some of the comments that you have received in the public domain about microwaves? Hello? Okay. In case you have not heard, about 4 or 5 years ago, there used to be a WhatsApp message floating around very widely saying that the Samsung is going to stop manufacture of cooking ovens by 2024 or 2025 because some laboratory in the US has confirmed that cooking food using microwave causes cancer. Okay. This is basically a fake message that is being sent to basically to harm Samsung or other reputed manufacturers of microwave oven. Okay. First of all, microwave radiation is dangerous when directly hits you, but inside a microwave oven, it is not at all dangerous, not only to the persons but also to the food that is being cooked. Okay. The reason why it is not dangerous is it is not a radioactive material. It is like a gamma radiation or anything like that. It is a very low energy radiation, and the energy of the microwave is so less, it cannot change the DNA of our body. Okay. And many other people think that when we eat microwave cooked food, it alters our DNA and also it causes cancer. There is no scientific studies that has been done to say that microwave cooking causes cancer or anything like that. These are all rumors floating around unnecessarily. Now you may say that I come from a company which manufactures microwave, therefore I am saying like that with a vested interest. No, that is not the case. Okay. First of all, we do not make microwave cooking ovens in our company. We only make it for other types of industrial heating. And the second thing is that I can prove it in the next few slides, why it is not dangerous, why it doesn't change the DNA, why it does cancer and other things. Okay. The second complaint, people talk about it, basically uninformed, unscientific people talk about it, is that microwaves destroy nutrients in the food. Therefore, what they are saying is that when you cook food, good nutrients are destroyed very easily in a microwave compared to conventional heating, like with a gas or induction furnace or induction hot plate and things like that. Okay, this also is not valid. In fact, cooking with microwave benefits the retainment of the nutrients for the simple reason that the amount of time that is required to cook the food by microwave is much less. Therefore, the food is not exposed to elevated temperatures for a longer period of time. Therefore, the nutrients are retained in the food. By the way, any type of food that is cooked at high temperatures of the order of 100 degrees or more, there is certain types of food, they lose their nutrients to some extent, irrespective of the method of cooking. Okay. But because the microwave uses less amount of time, the nutrients are not lost over a period of time compared to the conventional cooking. Therefore, microwave cooked food is pretty nutrients. Now, this aspect had some issue in the past for the simple reason that in Western countries, they have the habit of storing the meat, especially non-vegetarian food, in the refrigerator and then keeping it in a microwave for eating. Okay. And when they do like that, sometimes what happens is that the sufficient amount of time is not given for the item to be cooked properly. Therefore, certain portions of the meat is not cooked, which causes health issues later. Okay. And this has got nothing to do with the microwave itself. It is just the wrong usage of the wrong way of cooking the food. Third thing is that microwave ovens are unsafe and people can get exposed to the microwaves and so on. This also is not true. All the microwave manufacturers are make their products with a lot of safety in mind, and there is something called the Faraday cage, some kind of a metal screen, porous screen that is put on the window of the microwave, where the penetration of the microwave coming out of the chamber into the open is just not there. Therefore, microwave ovens are very safe also. Okay. And anytime that you hear something about microwave, please check with a technically qualified person rather than assuming anything. I'm very particular about these things because I keep hearing from many people about these points again and again over a period of time, and therefore I thought I will share this information about the myths associated with microwave in a scientific manner. Any questions, please? Hello? Okay, I'll proceed further. Okay. So typically, whether it is an industrial scale system or a household microwave oven, basically the components are the following. Okay, there are 3 or 4 important components which goes into the manufacture of the microwave system. One is the magnetron, which basically generates the microwave. In fact, this technology is quite complicated, and I think, to the best of my knowledge, most of the microwave magnetrons are imported into the country. I don't know about any defense related labs which make their own, but at least for the household kitchen type of applications, the magnetrons are usually imported. And I think even our company, Enerzi Microwave Systems, we also import the magnetron from outside. Okay. This is the one that generates the microwave energy. Then there is a waveguide. This waveguide is usually some kind of a metallic structure that allows the microwave to travel from the magnetron to the other parts of the oven or a furnace or whatever it is. Okay. And usually in this process, we want to ensure that the energy of the microwave is not lost. Therefore, basically, it is everything is kind of getting reflected without any absorption, and therefore the efficiency of transmission is very high. These waveguides are typically either rectangular or cylindrical in nature, depending upon the end application. The third part of the system is what is called the solid state generator. This is basically allows the control of the microwave power. In most of the systems, one will be able to vary the power of the microwave magnetron from very low to the maximum level. Okay, so these solid state generators takes care of that, and it is also allows the fine tuning of the frequency required exactly to 2.45 gigahertz. And the last component is what is called as an applicator, which directs the energy from the waveguide into the material or the object or whatever it is that needs to be processed. Okay, it's called as an applicator. Basically, these are some kind of a funnel type of shaped material, and this allows efficient and uniform heating of the object. Now, let us talk about some examples where the microwave is used for processing of materials. The first one is ceramics and composites. Okay. As I mentioned earlier, the ceramic means usually inorganic materials like aluminum, alumina or aluminum oxide, magnesium oxide, some silicates, porcelain, zirconia, titania, so on and so forth. These are all very high temperature materials which can withstand. Typically, the melting point of these materials is about 1500 degrees and so on. And one very good example would be, I can say, is the alumina substrate that is used in integrated circuits. Okay. You make a high alumina material, which is a very thin and extremely flat, on which you deposit your circuits. Okay. And that alumina material is also acts as an insulator for the rest of the system, electronic system, but also provides a conducting path for the heat that is generated in the circuit. And the strength of this material depends upon what is called as the microstructure. That means when you look at the sample in under a microscope, typically what is known as a scanning electron microscope, you will look at the what is called as the grains of the material. That means the particles are attached to each other with some particular size. This microstructure controls the macroscopic property of the material. For example, if you are, let us say that you are having a tungsten carbide material, and tungsten carbide is supposed to be extremely hard material, and it is also supposed to be very strong material. Okay. In order to get a very strong and hard tungsten carbide material, the microstructure has to be very fine. That means the grains of tungsten carbide as seen in a scanning electron microscope should be very small, typically of the order of 1 micron or 1.5 micron. Okay. If for some reason, if the processing is not done all right, and if the grain size becomes, let us say, 4 microns or 5 microns, that is double or triple that of 1 micron or 1.5 micron, then the hardness and the strength of the material is very much reduced. Therefore, it is becomes a poor material. Polymers. Somebody mentioned earlier that you are interested in making polymers, how to use the microwave. Typically, it is used for curing material, joining and degradation control. Okay. Many a times the curing of the polymers is done at elevated temperatures, and it is done for a fairly long time, let's say 150 degrees or 160 degrees or something like that. Okay. And the curing is done for several hours or sometimes even overnight. Okay. But with microwave, depending upon the chemical constituent of the polymer, this can be done extremely fast. Therefore, the degradation of the polymer is avoided. What I meant is that any polymer, when heated to elevated temperatures for considerable amount of time, it degrades. Okay, the degradation may not be visible immediately, but its properties are compromised. By using microwave, you can cure the material, but at the same time, because the time required is very less, the degradation is very much reduced. I mentioned earlier that metals and alloys usually reflect the microwave, and therefore it is difficult to process it using microwave. However, in the case of powder metallurgy, I'm sure some of you are familiar with powder metallurgy, where you may take the metallic powders and make some kind of a mixture, press it in a mold at high pressure, and then heat it to a high temperature. It has been found surprisingly that when metal powders are mixed and pressed, when there is a porosity associated with the metals, okay, it has a tendency to absorb microwave rather than reflecting. And this fact was known only in the last about 25 years or so, and therefore a large number of powder metallurgy components are being done using different metals and alloys. Okay, if you put a sheet of copper or a steel or anything like that into a microwave oven, it will reflect. But if you make it into a powder, press it into a pellet, when you make a pellet, typically still the porosity will be of the order of 25, 30, 40%. And when the porosity is present, the microwaves do get absorbed and heat the material, and then you can sinter that material. Okay, and so therefore metals and alloys can also be used with microwave. Then there is another very interesting application related to food processing. Unfortunately, in our country, this aspect has not got the importance it should have been taken by this time. Okay. If you go to any rural area, let us say, for example, in your area like North Karnataka, a lot of chili is grown, right? And during the season, what they do is they keep the chilies in the open sun for drying to make it into red chilies. Okay. So when you do that, typically it is dried for several days in the open sun. Of course, it is a very cheap method and nice method, but unfortunately, it gives rise to a lot of dust and other impurities and so on and so forth. And it takes a lot of time. And if there is a rain suddenly, then everything gets spoiled. But using microwave, if you can dry it, then the whole process can be done extremely fast. The other application in food processing is using what is called as the sterilization. Most of the food items do get some kind of a bacteria, other things, and they spoil the food. By giving a microwave treatment to the food, what happens is that all these viruses, bacteria, and other microorganisms are completely destroyed, and therefore the food will last much longer. This is being done very widely in Western countries. But in India, it is not being done to the extent that is required to be done. And last one is, as an example, I'm talking about graphene. I am sure most of you would have heard about graphene. It's one of the most wonderful material that has been discovered in the last 15-16 years. And one of the ways to make graphene, or the standard way of making a graphene, is to take a graphite material and inject it with some ions like potassium and other things in between the layers of the graphite, and then quickly heat it to about 900 degrees to 1000 degrees centigrade, so that the layers of graphite are separated, giving rise to graphene. Okay, and this process is quite time consuming, because you need to heat the material to 1000 degrees centigrade, and you cannot heat it very fast by conventional method. And we in Enerzi microwave system are able to do this task within less than 5 minutes. Okay, we take the treated graphite material, expose it to microwave, and within 5 minutes or even less than 5 minutes, okay, the temperature goes up to 1000 degrees centigrade and exfoliation takes place. Any question on this?
No, sir. No, sir.
Okay. Now there is one more issue that comes up, like some polymers or even ceramic materials are not when they do not absorb microwave, what to do with it. Okay, suppose I have a ceramic material and I apply the microwave, it doesn't absorb. Okay, then how do I sinter it? Okay, there is a technique for overcoming that, and I will talk about it a little bit later. So so basically, advantages of microwave processing as seen are, definitely it is a very, very fast process. Instead of using from cool to cool can be a 1 day or 8-hour shift, it can be done in a few minutes, or at best less than 30 minutes. Okay, energy efficiency is very high, and superior material properties. And I will talk about the microstructure in my next talk. As I have already mentioned, when you heat a material to a high temperature for a long period of time, like in 2 hours, 1 hour, like that, then there is a mechanism that takes place, what is called the grain growth. Okay, that means the grain that you see becomes bigger and bigger, and as it becomes bigger, the mechanical properties and transparency, optical properties and other things are compromised. Okay, and by using a microwave, you can avoid this grain growth of materials. Then there is a selective and localized heating. For example, if you can put some absorbing materials in a plastic, okay, you take a plastic and for some reason you need to make it into a mixture with some microwave absorbing material, then you can still heat the material. Now, let me talk about what exactly are the future trends in this particular area. One is what is called the hybrid heating technique. Okay, let me elaborate a little bit on this. Let us take a standard material called as aluminum oxide, which is a workhorse for most of the ceramic materials. Most ceramic materials have certain amount of aluminum oxide present in them, and aluminum oxide is transparent to microwaves. So when you want to sinter aluminum oxide, and when you put it in a microwave furnace, it doesn't absorb the microwave radiation, and therefore it cannot be sintered. Okay, so the one method for overcoming this problem is you take the material and heat it with a resistance heating up to about 600 degrees centigrade. That means you use electric heaters and heat the sample to 600 degrees centigrade and then apply the microwave. Okay, what happens is that at at about 600 degrees centigrade, the electromagnetic properties of that aluminum oxide material changes and it starts absorbing the microwave radiation. Okay. So this system is called as a hybrid technique. Okay. So you preheat the material with conventional method like resistance heating, and then once about 600 degrees centigrade is reached, you switch off that and go in for microwave radiation. Then you can take the sample to 1400, 1500, 1800 degrees centigrade also. Okay. So this is one method of heating the materials which doesn't absorb the microwave initially. Okay. Surprisingly, most materials at elevated temperatures become microwave absorbers, though they are not microwave absorbers at room temperature. Okay. So once you know this, then this technique can be used. The other way of overcoming this particular problem is that if you don't want to use a hybrid system, you use something called as a susceptors. Basically, let us say that you put a material, like in this particular case, aluminum oxide, you put it in a silicon carbide crucible. Okay. So silicon carbide absorbs microwave radiation, aluminum oxide does not. Okay. So when you radiate the system, the silicon carbide absorbs the microwave radiation and gets heated up, and after some time the sample in the silicon carbide crucible gets also heated up, and then it becomes acts as a microwave absorber. Okay. So this principle also can be used. I understand that nowadays the further refinement in microwave process is being done using artificial intelligence and machine learning. I do not know much about it, but artificial intelligence is going to invade into all aspects of our life, and it is no surprise that microwave technique also will be benefited from this new technique. And we talked about the magnetron, and I believe that there are solid state microwave generators are being developed, which will give much better efficiency and control compared to normal magnetrons. And I already talked about the superior absorbers and susceptors. Susceptors are basically materials that absorb microwave and gets heated up and pass on that heat to the material which doesn't absorb microwave initially. Okay. So in conclusion, I would say that microwave processing has already revolutionized the industries by providing faster, energy efficient and eco-friendly processing solutions. It is very, very widely practiced, and in my next talk, I'll give specific examples so that you will be able to appreciate it. And since most of the modern manufacturing processes require some amount of drying or heating, this is an ideal method compared to conventional techniques, and hopefully integration with artificial intelligence will spur further growth in this particular field. Thank you. I'm open for questions now.
Hello, sir.
Yeah.
Sir, would you please tell us about the metal processing in a domestic microwave oven?
Sir, I will certainly will not recommend usage of metals in the domestic microwave oven. Actually, one should not be experimenting too much with domestic oven because there is a very good possibility of damaging the magnetron when you use wrongly the microwave oven in the kitchen microwave oven. It requires some kind of prior knowledge or experience or theoretical knowledge before one can use metals in the domestic microwave oven. I will not recommend, sir, from safety point of view. If you see, if you put a metal into a microwave oven in the house, I mean in the kitchen microwave oven, you will see a lot of sparking that takes place. That is because there is a concentration of the microwave which gets heated and it gets reflected back into the magnetron, and the magnetron life is very much reduced. So I will not recommend that, please.
Can we directly expose metals in the industrial ovens, microwave ovens?
You can do that with some care, because you need to kind of embed it with some kind of protection for that. Like, for example, you put a powder, okay, some dielectric powder around the metal, and then expose it to the microwave. So you need
Sir,
to,
will it be affordable if we
Yes.
use?
yes.
Sir, what would be the cost of an elementary level industrial oven, microwave oven?
You are okay. There are two types of things are there. One is a microwave oven, and the other one is a microwave furnace. Okay. Microwave oven is typical for just drying any material for the removal of moisture and other things, maybe to 100 degrees or 150 degrees centigrade, and depending upon the application. If you are going for a microwave furnace, again it depends upon the temperature that you want, whether you want 1200 degrees centigrade, 1500 degrees centigrade, or 1800 degrees centigrade. Okay. I would say, just to give you an idea, I mean, the rough figure I am giving you, it also depends upon how big the chamber size you want to be and things like that. Let us say that you are using it for a laboratory research purposes, and inside dimensions can be of the order of, let us say, 8 inches by 8 inches or by 8 inches. Okay. And the temperature you want is about 1600 degrees or something like that. I would say it is about 18 to 20 lakhs. The initial investment for a magnetron is on the higher side, but you will recover the cost very quickly, because your power consumption, the cost of electricity and other things, it will be very much less compared to that of a conventional resistance heating based on heating elements.
Okay, sir. Thank you, sir. Actually, sir, I have gone through many research papers,
Yeah.
and they used a domestic microwave oven, which you have mentioned as kitchen oven,
Yeah.
in their research.
Yeah.
So I was thinking about that only.
This is
Thank you.
even I have used it about 25 years ago, when professionally done microwave ovens were not available. Okay, what people normally do is they buy a microwave oven and drill a hole at the top and drill a hole at the back side, put some
Certainly, sir.
thermocouples, and do that type of exercise. I will not recommend that right now, because microwave professionally done laboratory scale microwave ovens are easily available now. There are, when you use it domestic microwave oven, there are two possibilities are there. One is there is a possibility of a leakage. Okay. Then the second thing is there is a possibility of damaging the equipment itself while drilling holes and things like that. So, and the alignment of the magnetron can change, and so many things can happen. But many years ago, people used to do a lot of laboratory scale experiments using domestic microwave oven.
Thank you, sir.
Sir, there are a few questions in the chat box. You can just check it. One or two.
Can somebody read it, please, for me? I will prefer to answer.
Hello, sir.
Yeah.
Good evening, sir. Good evening,
Yeah.
sir. This is Rayappa Mahale, sir. I have one question, sir.
Yeah.
How that microwave sintering is differ from spark plasma sintering in case of grain growth suppression, sir, hindering the grain growth.
Okay.
Growth.
You see, let us take one example. Okay.
Yes.
Let us take aluminum oxide. Okay.
Okay, sir.
Let us say that you are studying some property of aluminum oxide. You press a pellet, okay, in a mold, what is called the green pellet. Okay.
Correct, sir.
And when you do that, at best you will get about 45% of porosity will be there in the green sample. That means as you press it. Okay.
Okay, sir.
You take the powders, let us say you take a 1 micron or less than 1 sub-micron powders of aluminum oxide, high purity.
Yes, sir.
Mix it with some binders like some wax or CMC and other things. And you put it in a mold, apply a hydraulic pressure into it and make a pellet. Okay.
Yes, sir.
That at best can have about density of 55% of the theoretical density. Therefore, 45% will be porosity will be there. Okay.
Okay. Yes, sir.
Now, when you start heating it, this pellet for sintering purpose, okay,
Yes, sir.
then what happens is that initially at about 110 degrees, 120 degrees, whatever moisture that is present will go out of the sample.
Yes, sir.
Correct?
Correct, correct, sir.
And then when you go to about something like 250, 300 degrees centigrade, the carboxymethyl cellulose or any other binder that you would have used, like polyvinyl alcohol, PBA,
Correct.
and other type of binders are being used, they all go around 400 degrees centigrade. Okay.
Correct, sir. Yes, sir.
So at that stage, the porosity actually increases because all these materials are gone now. Okay. They all leave behind the pores.
Yes.
So once you reach about 1200 degrees or 1300 degrees centigrade, right?
Yes, sir.
The particles of aluminum oxide, there is a diffusion process that begins. So from one particle to other particles, there is a diffusion of aluminum oxide that takes place. That is called as the actually sintering mechanism.
Correct, sir.
Okay.
Yes, sir.
So over a period of time, slowly the porosity now will start decreasing and the sample shrinks in size.
Yes, sir.
Typically, I would say for submicron particles, the shrinkage can be as high as, I don't know, 12 to 15%. Okay.
Yes, sir.
So as I mentioned earlier, in order to sinter it fully, because you want to get a fully dense material, you need to heat it to a high temperature and at the same time to keep it for a long period of time.
Yes, sir.
Right?
Okay, sir.
So when you keep it for a long period of time of the order of, let's say, 2 hours or 3 hours, the diffusion process is dependent on temperature. Therefore, the diffusion is very high. Therefore, the grains, the bigger grains will start growing at the cost of smaller grains. Correct?
Yes, yes, sir. Yes.
Okay. So after finishing the sintering, so you will have a dense material. Let us say it will have about 99% theoretical density with about 1% of porosity with either open porosity or closed pores.
Yes, sir.
So when you look it into the microstructure under a microscope, you will see grains of the order of 5 micron or 6 micron. See, you started originally with submicron powders. And because of the diffusion mechanism, the grain growth takes place and it will be of the order of 4, 5, 6 microns.
Yes, sir.
So when you have that, that is called as a grain growth. Okay.
Okay, sir.
Now, when you use microwave, you will see this example in my next lecture. Okay.
Okay,
The
sir.
temperature that you require to get the fully sintered material is not 1600 degrees centigrade for 2 hours. It will be at 1400 degrees centigrade for 30 minutes.
Correct.
Okay.
Yes, sir.
So there is a lesser time and temperature involved for diffusion.
Correct, sir.
Therefore, grain growth doesn't take place.
Okay.
But still, the full sintering takes place.
Yes, sir. Yes, sir.
So, because the temperature is lower and the time for sintering also is lower, there is no chance for the too much of grain growth to occur.
Yes, sir.
And therefore, the sample will be of a better quality.
Okay, sir. Sir, every whatever you explained, everything will be before it will reach us the recrystallization temperature, right, sir?
What do
Sintering
you?
is always we are doing means below its recrystallization temperature. Above, we can, if we go above recrystallization temperature, then again
It depends on it depends usually on the system.
yes, sir.
Okay, it depends on the system. Sometimes, you know, they put what is they are in aluminum oxide, for example. They
Yes, sir.
always put a little bit of magnesium oxide as a what is called the grain growth inhibitor. Okay,
Inhibitor. Yes, sir. Yes, sir.
it is very widely used. Okay,
Okay, sir.
typically about some 0.25 or some such percentage is used. Very fine magnesium oxide.
Yes, sir.
This magnesium oxide is there in the grain boundary and prevents the grain growth. Okay,
Okay, sir.
and typically 2/3 the melting point is considered as the temperature at which is required to sinter a material.
Yes, sir.
Right? For aluminum oxide, the melting point is about 2000 degrees. So at least 1200 degrees centigrade is the temperature at which the sintering mechanism starts happening.
Correct, sir.
Coarser the material is more difficult to sinter.
Correct, sir.
Similar type of thing happens in all other materials also.
Yes, sir.
Hopefully, I hope I have answered your question.
Thank you, sir. Thank you, sir, for the detailed information.
Yeah. And you will see in my next talk some specific examples.
Yes, sir.
And you will be able to appreciate the benefit of the microwave technology later.
Sure, sir. Thank you, sir.
Yeah. Any other question, please?
Okay, any other questions from the participants? Okay, if there are no questions for this session now, we will take a break of sharp 10 minutes.
Yeah.
And we will get back so that we will give some break to our honorable speaker.
No, I don't need any break. Actually, I can go on.
So 5 minutes.
But it's good to take a 10-minute break.
Yeah.
And because I think most of you are sitting in a class for a long time, and it's very difficult to be a student for faculty members.
So
okay, let us meet at 7:50.
Yes, sir. Yeah, sharp at 7:50 we'll meet, sir.
Okay, fine. Thank you.
Yeah, we will keep the meeting on only. Only recording will be off. We can keep ourselves logged in.
Okay, fine. Okay.